Hi everyone, and welcome to Schrodinger's Bathtub with me, Jan from Jen's the Corner, and the absolutely wonderful Matt, almost a doctor. We were laughing when we came in because I just said to Matt that if I've done this right, the intro should now have his name on it, and it didn't, so which means I did it wrong. There's always some fault. I'm not perfect.
But see, that's how you know you've got a stream, is when there's a technical problem.
Yeah.
So of course we're ready to go
and
because we've had at least one technical problem.
Now, I know you're all waiting to hear from Tessa, the astrobiologist who's coming to join us. She will be on a little bit later. It is very early where she is, and it's really nice that she's coming on and having a talk with us. But we thought we'd get going at this time so Matt and I can sort of introduce what the topic is, and then once she's in here, we can throw her some questions because that'll be fun. So, hi to everybody in the chat. To Jade, to Purple, to Jay, Chris, Donald, Harmonica Man, Greg Harwick. I'm losing track of who's actually in there. Did I say Chris?
People.
People. All the people in the chat. To Randolph, who was very, very eager. And Dog. Thank you, Dog, for being there. Yeah, so, Matt, I'll let you go.
Also, questions are welcome at any point in this stream. Feel free to use the chat.
We will both try to keep track of the questions. Of the questions, but we're not good at it.
But we will try.
We will try. We're very trying.
Where to start? Well, I guess my starting point for today's topic is the fact that the oldest science out there is astronomy, and one of the oldest questions in astronomy is, are we alone? Is it just humans? Are we the only intelligent life? Is this the only planet with life? And these questions are understandably complex, so we have to start somewhere. I'm trying to make a video about what life in this solar system would look like, and it's taking a long time to get the research because it is complicated. And one of the phrases that comes up is life as we know it. We have to actually know what we're looking for, which is why it's always interesting to talk to an astrobiologist, because sometimes what we think of as life, or we think of in movies when we see aliens, your almond-headed, little green men, or now I'm trying to think of all the other movies that we've got aliens in, including coming out of people's chests or hunting people down in a forest, something like that. But chances are what we're going to spot is going to be some weird little chemical system that's similar to like bacteria here on Earth. In fact, life's been proposed on many places in our own solar system. And so not only that, but we also look for Earth-like planets elsewhere. But the more we find out about the universe, the more we realize life may not need an Earth or an Earth-like planet to survive. So the question keeps getting broader and broader.
Yeah, and Purple, yes, it's life, Jim, but not as we know it.
Yes. I still like the Monty Python line that is, you better pray there's intelligent life somewhere up in space because there's bugger all down here on Earth.
It is a brilliant line. It's a brilliant song too.
Yes. It has to be updated a bit because we found out the universe was actually bigger than they thought at the time when that was written.
The galaxy is wider across the bulge than when they thought it was at the time, and there's a whole heap of things. But Brian Cox's version with mental blank, and he's Australian too.
Tim Minchin.
Tim Minchin, thank you. Where Tim sings the line and Brian goes, approximately. It's brilliant.
Yes,
so,
I think though. Most people do think of alien life as being that kind of intelligent form, as I mentioned in the movies. But like the question I've been thinking about recently is like, what would probably be the closest place to Earth that we would find alien life, extraterrestrial life? Because I don't think the moon would do it. So we have to go. So the nearest close, like, large body in the solar system is Venus.
Yeah. Oh, well, I mean, there was thoughts earlier this year that they may have actually found life in Venus because they'd seen those trace elements in the upper clouds of Venus that they thought could only be there as a byproduct of life. It turns out later on that the readings that they got for those chemicals wasn't accurate, which means there wasn't abundance of it, so it was unlikely to be life. But it is one of those things that life doesn't have to be on the surface of a world. Life can be microbial and floating around in clouds. And the upper clouds
it does here.
in Venus, yeah, it does here. So the upper clouds in Venus are actually cool enough that you could conceivably have life, and there's less acid in the higher up you are. And we have life on Earth that lives in fairly acidic areas. I mean, obviously, these are things that Tessa could answer much better than you or I, Matt, but it is absolutely fascinating, the stuff that you get out there.
Yes, we gotta set things up so we're ready for that. Also, I think we have a guest in the chat, but I do want to remind our guests to stay on topic. But I think Chris is chatting to him. But I haven't actually spoken to this guest yet. So hello there, Darth, if you're in there. Keep it to aliens today.
Yeah.
But
and
yes,
if Darth gets
point.
a bit rude, feel free to give him a little timeout. Because I'm not going to tolerate that. I've got a spanner
too. I'll keep an eye on it. But,
well, we've got Kitty and Chris and Purple there, so I think they'll keep track of it.
Someone will.
So, yeah.
But yeah, that paper that you're referring to was the findings from September 2020. That paper came out.
Yeah.
I remember I've actually read. I haven't read all of it. It's a long paper. It's like a full 20 pages, which is quite long for a science paper. And because it's not to do with my PhD, I haven't bothered to read all of it. But I did read parts of it. I did read the part where they said the life, and I think it was more of this is one possibility. It's not the only one. And what it was there isn't a known chemical mechanism that should produce phosgene, or PH3 is the chemical.
Yes.
So you've got one phosphorus and 3 hydrogens attached to it. Because in in an atmosphere like that, particularly one that has a lot of acid and some oxygen floating around or oxidizers, it should be broken down, so there shouldn't be much of it. And so this paper noticed, hey, there's all this phosgene around, or at least it looks like there's the color of phosgene around.
Yes.
So they're looking for the particular, I think it was an absorption line in the atmosphere, because it won't be emission at those temperature. And they were like, oh, there's enough of it that this probably isn't natural. But as Jen was saying, it turns out they made a mistake in the background reading. Yeah. Which is something that I've done myself, but it's pretty obvious when you do it on Earth. But when you're trying to detect things on other planets, it's very sensitive.
Yeah, so basically,
it was probably about a 20th or like 1 part per billion of this stuff, which is not enough to suggest there's actually life.
And it is really hard to pick that out because you've got a lot of other signals in amongst the absorption line signals. It's not just like when you're first learning about absorption lines in the lab, you're shining a light, or you're reflecting a light off one particular type of gas, and you're seeing what the absorption or emission layers are. And you'll get the couple of lines, and they match up perfectly to what's in the book. But when you're doing it to the atmosphere of another planet, you're trying to see sunlight that's bouncing off the atmosphere, coming back to you, and then trying to pick out in amongst all these different elements which ones are actually in there. And it is quite hard to do because you will get, even though different compounds have different absorption spectra as well, you can get ones that can look very, very, very similar. So like the elements themselves are very different, but compounds can end up looking very close to each other. So
I'm just looking at Chris's message, so Heretical's message there, and we might need to explain something else. So I feel like I jumped into this a little too far, but one of the ways you look for life is not look for the life itself, because it's hard. Yeah, we've only been to a few places in this solar system, let alone outside this solar system. And so you employ a technique called spectroscopy, or a specific type of spectroscopy that's known as absorption or emission spectroscopy. it gets very complicated quickly, but every element and every molecule has very, very specific colors that it takes in and gives out. Yes. So most of us are familiar with the little drawing or a picture or a photo of having white light going into a prism and then you have it splitting into a rainbow.
Yeah.
So if I took a light source like the LEDs sitting next to me, or the both of these, the lights next to me are LEDs, and if I took that through a prism, it'll split up. But if you're missing colors, they don't show up. So you can split them. And if you have like a mercury lamp or sodium, if anyone's seen the old street lights, the orange ones, if you put those through, you'll end up with a couple of bands. You'll end up with a faint green one and then two very bright orange colors, very narrow, so next to each other. And so sodium is the only element that has those colors. Goes the other way too. They will absorb certain colors as well, so that if sodium, mercury, hydrogen, phosgene, as we were mentioning, pretty much any molecule with some color, and when I say color, it doesn't even have to be visible, it can be infrared as well. Some in the UV, which they're also looking at for Venus, but most of the ones I've seen tend to look at IR because it's a bit easier to do. That's actually what my PhD is using infrared spectroscopy to spot methane and concentrations. But what you do is you look at the atmosphere of other planets. And so you try and spot these little colors that are missing that indicate you've got one. And one of the common ones thereafter is oxygen. O2 is not stable because it'll normally get broken down into other things. It'll react with chemicals in the rocks and it'll rust. So normally if you've got an atmosphere of oxygen, there's life on the planet. So the idea is to try and build telescopes sensitive enough to spot these colors on exoplanets in other solar systems, which at those distances is insane. But that's what they're doing. And even Venus, the closest planet to us in the solar system, we're still having trouble with because it's not that easy. And some measurements have suggested that it could also be different areas of Venus that they're looking at with these. Or it might be cyclical, but yes, if the original measurement looks like it's in question, so that one's not looking as sorry, I got distracted by the chat.
Yeah, I've been distracted a little bit
too.
It's not
just Venus that we're looking at. So I know they're also looking at Jupiter because it looks like there's actually maybe enough water in Jupiter's atmosphere as well to harbor life.
Yeah,
possibly.
This has actually been considered since about the 70s that when they were first doing
and then recently
they
had more confirmation, wasn't it?
Because they know now from the various probes we've had around Jupiter that the upper clouds are actually warm enough that not only is there water there, but you'll have liquid water, not ice water, and they're warm enough that there's enough energy within Jupiter's upper clouds to actually sustain life. And because you've got all the different chemical reactions that can happen within those clouds. I mean, you've got incredibly fast winds too, which is not necessarily the best environment for life, but you've got the potential for it. And that's absolutely fascinating that you could actually have life in a gas giant. I mean, it's not going to be anything like we see here. And we will ask...
no.
And we will definitely ask Tessa about it when she gets here. But it's a fascinating thing that you could consider that there might be a life form there that looks maybe possibly a bit like a jellyfish, but designed for floating in these high winds in the upper atmosphere of Jupiter, and they basically just sail around the planet, which is absolutely fascinating. So we've still got Darth in the chat being a bit of a Darth, but...
Yeah, I was tempted to mention that. All I'm going to say to Darth is this show is about science. We're not touching religion here. Feel free to ask us questions. If you want to ask us, about chemical questions, spectroscopy is my area of expertise. We'll have our guest on soon, hopefully, where we'll be talking, astrobiology. So if you have any questions about that, feel free to answer. We won't stop anyone like that. But again, if they're off topic, we we'll probably for the most part ignore them, and you might get timed out. So just a warning there.
Yeah. Our
but a friendly one
moderators
too.
will
Like-
be right on top of
Like
it.
try us with the any science questions you want. I don't mind. We're here to today's more just kind of speculating what life will look like based on the science we do know. So yeah, and also that goes for anyone in the chat. Try us.
And the Bible's not a
and
science
no-
book. I'm sorry,
Yeah,
Darth.
yeah.
The Bible is not science.
Yeah,
At best, you could call it history.
Yes. And as you're saying, we're not going near religion. So even if it was, it has nothing to do with this show. We're just
Yeah.
here for science. So that keep for the other shows. If you want to chat that with me, I think both Jen and I, we're on Hereticals sometime soon. I think I'm
next
next
Friday.
week or something. Yeah. So you can chat with us then. I'll happily talk to him then. But for now, let's keep going with this. And this has, although on his last comment, something to do with evolution, but that's our point here. We're looking for chemical systems that may not match the life that we've got here.
Yes.
But it was funny you brought up Jupiter, because one of the other places that's quite likely for life are the moons around Jupiter.
Oh, yes.
And Saturn, which are very similar. They're too cold for liquid water, or you would expect them to be, but they're not. They actually get extra energy from gravity. So just like Earth has tides that move around and slosh around as the moon goes around the Earth, those same forces can work in reverse for Jupiter's moons. As they go around Jupiter, they actually pick up energy in the form of tides. And they reckon for a few of the planet, I think Enceladus, Ganymede is some of them.
Yeah.
Although I'll probably get confused between Saturn and Jupiter, because they each have like 60 moons and 50
something like that.
moons. It's a lot of them.
Enceladus is the one
some
in
of them-
Saturn. So yeah.
Yeah.
It's,
I think Ganymede is Jupiter then.
Ganymede
but-
and Europa for Jupiter. Yeah.
Yeah. Oh yeah, Europa's the other
Europa's
one. There is
the
a
big
sci-fi
one.
movie on Europa.
Yeah, there is.
Yeah. There is enough energy to actually have inside, so under like a surface layer of ice, to actually have liquid oceans, which is really fascinating, because once you get water with a few chemicals, sulfur, phosphorus, a couple of others. I know there is sulfur in, I think it's Enceladus or Europa, because we've actually detected it.
We've
done a fly
we've
through with
actually,
the
detected amino acids in the plumes from Europa.
Yes.
So,
We've
and once you have
actually
amino
detected the
acids,
building
you've got the
blocks.
building blocks of life. So
Yeah, that doesn't mean there is life, but
No.
what it shows us is that maybe the requirements for life are much easier than we thought. In fact, we found some of the building blocks of life on comets as well, but where they get it from,
now Chris has asked us an interesting question that I think we should answer.
I think it's actually most of the ones we're talking
Most
about.
of the ones
I think
we're
most
talking
of them-
about. Enceladus,
Yeah, so-
Europa, Ganymede, even Pluto is suspected
Io?
to have.
Yes.
No, Io's all
underwater
volcanoes. There's probably very little water on Io.
Might be enough. But Io, I think they have thought about it. It's got giant volcanoes
It
on it.
does.
But as you're saying, Pluto,
Even Pluto,
when
yeah.
they finally did the fly past the other year of Pluto, there's a whole section of it that appears to be much thinner, that it looks like it might have liquid water. And again, it's very complicated. It's kind of those gravitational
because you've got
effects
two.
that add
You've got the
just
two
enough
moons
energy.
that are locked, facially locked in orbit, and my brain's gone. There's a word for that.
Tidal locking.
Tidally locked. Thank you. That are tidally locked, but you've also got the other two moons that orbit in the system, and between those, the weird gravitational interactions actually warms parts of Pluto. Not entirely melt the core, but it warms sections of Pluto, and it's enough. They think that there could be liquid water or liquid methane, possibly even lakes on Pluto. And liquid
they
methane
don't
is still a fluid that you could have life in.
Yes.
It'd be very different to
not
what we have, but
I
it's
think it's
possible.
less likely though, because it's not polar, so you don't have as much. You can't get as much complex or structure to some of the things. But again, that's saying that based on what we have here. And I actually have spoken to. They're actually a guest at the university when I was doing my honors for chemistry. who works down at the Australian synchrotrons. That's where they smash X-rays into samples and seeing how the X-rays bounce off to figure out what the chemical structures look like. And one of the things they look at are chemical systems at the temperatures you would find on Pluto and Europa and Ganymede and all that. So her research was what goes on in these planets from the synchrotrons. Really, it's quite cool. And one of the things that so I was asking her about the likelihood of life on other planets, and she was mentioning that we have quite a few of the. Oh, sorry, notice I got a question. Come back to that. Do we start out spectroscopic measurements outside our atmosphere, or do we have telescopes and ground and look through it? Actually, that's a good question I want to get to before this, because it does talk about how we do it. It's the answer to that is both.
Yes.
So if you're doing from the visible, if we're doing certain parts of, say, microwaves, ultraviolet, UVA, UVB, so close to the visible end of it, you can do from Earth. So, but the problem is the atmosphere does absorb certain wavelengths of light, so certain colors, and not necessarily in the visible, but particularly in the infrared. So there are certain parts in the infrared that our atmosphere just becomes like a black blanket. We can't see through it. So you would have to do those from satellite telescopes that are floating outside of it. Or you do like a flyby probe. So you actually have to send something past it. The best way to find out what's on these planets is to do a lander. So far, we've landed on Venus and Mars. And that's, I think, about it. I don't think we've landed on much else other than got the asteroid. But we've not landed on Mercury. We've crashed things into Jupiter and Saturn. I know we've done Saturn. That was recent. That was Cassini, wasn't it?
Yeah.
I think it was
Cassini and the Huygens
that we crashed into it.
We took.
Recently. So you have to put something there working with. I can't talk.
Oh, Matt, we're losing you. We're losing you, Matt.
Am I back?
Yeah.
Am I back?
Yeah, I think you're back.
It's weird. Normally it doesn't drop out this time.
All right. So it's the Huygens probe that was attached to Cassini. As Cassini was orbiting around Saturn, it got close enough on approach to Titan that it released this small probe that descended through the atmosphere. So we actually know quite a lot about the atmosphere of Titan. And we also know that Titan has lakes of liquid methane. And the same, like with Pluto, it's quite possible to have life that has evolved in liquid methane. We think it is possible. There's no reason why methane can't take the place of water in a living creature. I mean, of course, the chemistry of that life would be very different to what we have here. But
and it wouldn't survive very well.
We wouldn't survive very well there either.
But I guess this comes back to the point that the main thing, from my understanding, that my scientists are looking for is chemical systems where you have some circulation of material, where you can allow these processes to develop. And so that's why they're so interested in spotting these chemicals and also spotting these oceans. So like in Pluto, where it's actually insulated by a giant gas band of methane, they reckon that might insulate it so it doesn't frozen yet, but that extra energy it got from gravitational effects is enough to have a liquid ocean. Yeah. Which would be if you had life out on Pluto, it shows that you may not necessarily need to be anywhere near the sun.
Yeah.
Which extends the boundaries out much further.
But between what's happened with Pluto and what we can see with Saturn, there's quite a possibility that there could be rogue planets, especially gas giants that have gone rogue, that have their own moon systems that are floating around out there in the middle of space. We don't know where they are. But the gravitational energy that's in those systems is enough to sustain life on the planets. And that's an absolutely fascinating situation, that we could have where where we could have life just out there with no star at all.
Yeah, and I guess that's the more we realize the conditions are quite broad. But one of my favorite answers I ever got from talking to someone of this was when I spoke to that professor I mentioned earlier, and I asked her, so what you think, because at the time there was a lot of interest in Mars, a few years ago. I mean, there still is interest, but it's shifted a bit outside of Mars as well now. I asked, so what do you think the chance of life being on Mars? And she's like, there's a good chance that we put life on Mars because we didn't properly sanitize the early probes that went there. And bacteria on Earth has a really, really, really high resistance in some environments.
Yeah.
Like they went to the bottom of the ocean on one occasion and drilled a further 2.5 kilometers down and still found bacteria that was living. So you can find life pretty much everywhere on Earth, which suggests that there are chemical systems that will allow some form of life to exist elsewhere. It's not unheard of that some bacteria hitched a ride on one of our landers to Mars.
Oh, well, the same. Well, and we know they survived because we've had bacteria that hitched rides with the Apollo missions all the way to the moon and come back again, and they were perfectly fine. And that's bacteria. And we also know that, and we will mention them, tardigrades. We also know that tardigrades can survive in space as well, which is quite amazing for a multicellular creature that can actually survive in space for a fairly decent amount of time. Yeah. Tardigrades actually put themselves in a kind of suspended animation to survive it. So and then they revive later.
Yeah, you can freeze them. You can pretty much boil them. I think get them at 80 degrees. You can put them in the vacuum of space. All sorts of weird and wacky things, and they'll survive. But I just saw Nerdy's question as well about couldn't we tell if life we found on Mars had evolved there was actually from Earth? Yeah, we'd probably, particularly if it had some form of genetics, RNA, DNA, or anything similar, probably be enough to tell us whether it likely did. And if it was life similar to bacteria we found on Earth, particularly if we found it near any of our rovers, I think we'd be able to tell that it was from Earth because we have mapped quite a few genomes here. A very big giveaway would be if it used an energy system that wasn't found on Earth. It was not it was a really unique kind of chemical system to get its energy supply. So if you think on Earth, most humans, we need glucose, cellular respiration, and then trees, photosynthesis. There's other systems on Earth, but there are
it's
some
almost
that we
guaranteed
could
that if they don't use RNA or DNA, it's probably we haven't seen other forms of life develop on Earth. So if it's something different to that, then it's almost guaranteed that it evolved elsewhere. However, if we do see life with RNA and DNA on it, that doesn't mean that it didn't evolve there instead of here, because I mean, we know how evolution works. What we don't know is exactly how abiogenesis works, and life on Earth could have come from anywhere. Life in the solar system may not have even developed initially on any particular planet. It might have developed in the proto disk because there was enough warmth in there to have life first develop in the proto disk around the star, the young sun, and spread out to the entire solar system. So every bit of life you find in the solar system might have RNA and DNA. Every bit of life in the galaxy could have RNA and DNA. It's just the way it is.
Yeah, it's possible. One of the things too is that there is evidence that life on this planet existed a lot earlier than we originally thought it could. So that's not unheard of. It's also possible because Mars and Venus are quite close that panspermia could have been a thing. So I think both Mars and Venus, if you go back about 4 odd billion years, looked very similar to Earth.
They did.
They had oceans. They had atmospheres that probably weren't too, at the time, dissimilar to ours, or at least a prebiotic Earth anyway. And
early
we
Venus
know Mars had large oceans.
Early Venus probably had a day very similar to the Earth. Venus actually used to rotate the in the same direction as the other planets. It's actually been as its atmosphere expanded, it created a braking effect, which eventually slowed it down to the point where it's retrograde compared to other planets with its orbit. So yes, planets. Venus. A long time ago, a really early solar system, Venus probably had water and was very similar to Earth because the sun wasn't quite as bright as it is now as well.
Yes, yet evidence suggests that even though the sun wasn't as bright, the Earth has actually maintained its temperature fairly well. It wasn't as cold as we initially thought it would be given the sun's one, so it might suggest there's a bit more to it than we thought. But yes, the sun is slowly getting brighter and will continue to do so until it goes it can't go supernova. Our sun's not big enough. What it will do is it will start burning the last of its fuel up, and it'll get really big. And I mean really big. It'll go from where it is to a size roughly about where Earth's orbit is. So the ball will
It won't necessarily consume the Earth because when it expands, it actually pushes the planets out.
The intense radiation will blow Earth further away, and
of course,
so it won't get
no one will be here by then. Nothing will be on this planet by then because that push out will actually blow all the atmosphere off the planet as well. So, and burn it to a cinder. But hey, in answer to Harmonica Man's question, I actually don't know. I'm not a biologist, but I would imagine they are kind of keratin or something similar. It would kind of make sense.
That's small. That's too wild to me. Like, there's a lovely picture. I'll see if I can find it that sums up biology to a physicist. But my favorite diagram in physics to describe my understanding of biology was a little Cartesian 3D like coordinates X, Y, and Z with a big sphere next to it, and it just said, and had the caption down the bottom, "A cow centered at the origin," because that's physicists do tend to simplify things. Like, to me, you could put arrows and say, "What's this? What's this? What's this?" And I just look at it, go, all of that is tardigrade. But yes, it's an interesting question. I should have a look at that one. But they're pretty impressive. They can survive a lot, tardigrades. But my guess is if we do find life on other planets, it'll be even simpler. It'll be close to like the basic simple bacteria that we get here, some of the extremophiles.
I love how Nerdy likes to throw us the curveballs.
That's go beyond what I've covered. Where's Google? Give me a second. But yes, that's what I want. Questions. Push us.
The reason why Nerdy's stumped us on that particular one is that is a very new paper, and I actually haven't read it. All I saw was a video that somebody else did on it, and I'm struggling to remember it. But it has to do with a way that it has to do with the way that certain stars, when they get to their larger sizes, can actually like really large stars, instead of doing a normal supernova, they can throw off large chunks of their shell, but still remain a star afterwards. So they don't. So they still basically they do a supernova, but without being a full supernova. I believe that's what Nerdy's talking about because I've seen several things.
Yeah, it's fairly new to me. I wish I could talk on that one. It sounds fascinating. But see, here's one of the things. One of the reasons one of the ways we figured out the distances of our universe, because anything outside our galaxy, we can't just use how the Earth moves around the sun and kind of map how everything moves. Outside our galaxy, we can't tell distances. It's too far for that method.
Yeah.
It's the same as if you hold your thumb up in front of you and close one eye and then switch, your thumb will appear to move. And we can do the same for things as the Earth goes around the sun, but it won't get us beyond the galaxy.
Yeah.
So if we're looking at other galaxies and we want to map things, particularly even further out in our own galaxy, it becomes more difficult. Then you use what are known as standard candles.
Yes.
So what it is, it's an event that occurs in in astronomy. They occur every now and then, and they're the exact same brightness and the exact same color. So you can tell two things. It's like headlights coming towards you. The further away they are, the dimmer it is. But also, because we get blue and red shifting based on whether it's moving towards us. If it's coming towards us, it'll be blue or bluer. If it's moving away from us, it'll be redder. It's just how physics works. It's the same as when you have a siren pass by the front of you. It'll sound different when it's coming towards you away. Yeah, the Doppler effect. The same thing happens. So we can actually map parts of the universe that way. We can see whether they're moving away, and it also tells us how far, because we know roughly how bright these things are. We know what color they are. We know their brightness. We don't know what causes them. They're
well, we do know some of the standard candles, like type
I
1A,
was thinking the type 1A not supernova, the mini nova,
the mini novas,
type 1A. Yeah.
Type 1A
we don't know what they are.
Yeah.
Yes.
So we've got there's a couple of things that can produce standard candles. One of the ones that we know can happen is when a neutron star is orbiting another star, and it's close enough that the neutron star is siphoning gas off the other star. There's a limit called the Chang thingy. I can't remember. I hate it when I do this to myself. The Chandrov limit. Thank you, brain. You got there eventually. Yeah, the Chandrov limit, and it's a certain amount of mass that a neutron star can get to before it will go nova, and it's within a small threshold. So we know exactly.
Was it a black hole?
No, black holes don't go nova.
No, I'm talking about the limit, though. I thought that was the limit for a black
hole.
No. Although I could be wrong.
No.
That's a different one. Sorry, no.
Oh, well, look, I'm not an astrophysicist either, but we are for all these questions, we are actually having an astrophysicist on in a couple of weeks, and we are also having an astronomer on as well, so we can ask these questions so people actually know what they're talking about. But
if we wait, I actually think I have at hand my notes for this from when I did senior.
Oh, cool, Matt. We don't have to look stupid then. No, I think it's the Chandrov limit anyway. Probably somebody in the chat will, if Dave was there, who could be correcting me and go, "You're an idiot, Jen." Yeah. But basically, when the mass of the neutron star reaches the limit. Wow. When the mass of the neutron star reaches that limit, it will go nova, and that nova is, we know exactly how much mass is involved with it, so we know how much energy is given off, so we know exactly how bright it will be, and we can tell that it's that. And those type of novas always have exactly the same chemical signature to them. So we can tell it through spectroscopy exactly that it is that type of nova. We know exactly how bright it is and everything. So that is one of our main standard candles, because we know exactly how it is. They don't happen all that often because there aren't that many neutron stars orbiting that close to other stars that they can drag the thing off. But they happen often enough that they've given us guides to measure other distances and calibrate other standard candles that we use. So it's
is
been
that the one you're referring to, or have I got a different physicist?
What does that say? I can't read that. Sorry, Matt. You're gonna have to read that.
I'm terrible at pronouncing the Chandrasekhar mass.
Chandrasekhar. Yes.
That's for the black holes. Maybe
that's the black hole. Okay, so what's
confused.
the neutron?
Yeah.
What's the neutron star?
There we go.
But look, I had an entire lecture on the binary stars like you were talking about.
Oh, yeah, cool. Like so what is it systems. Called? What is the mass called?
The mass that we get to... Oh, I just...
what is the name for it? Because I know it does have a name, so I've confused the two different ones.
Chandrasekhar mass is how heavy you need to get within a certain volume before
to get a black hole.
Black hole, yeah. Because at that point, it cannot sustain itself. It collapses. And in fact, that actually brings me on to another point, because we're talking about life. And we think
before you do that, let's correct me. and say what the name of it is when with the mass on a neutron star when it.
That one I have to double check, actually. I don't like correcting people if I myself could still be wrong.
Oh, okay, that's right. Bear in mind, if we don't correct ourselves here, when we have the astronomer, I nearly said astrologer, the astronomer on or the astrophysicist on, we will get corrected. I will guarantee we will get corrected.
Yeah.
If not by people asking us from the chat to get corrected, we will ask anyway, get ourselves corrected, because I like to be right about these things, and I know, and as Matt said, I was wrong then, but I know it's something similar, because a lot of these limits and stuff were named after certain Russians, so
Yeah, it's too many. I'm terrible with names of people I've met, so yeah, this was a few years ago now. I did that, but the point I was getting to because you're talking about neutron stars, is when we think about the elements that we have access to in this solar system, particularly those on Earth, but also those on asteroids, Mars, Venus, etc., the ones closest to us that we might want one day think about actually mining. We're often taught that a lot of the heavier elements, particularly anything larger than iron, will have come to us from previous supernova. A star died for us, it had to. But maybe not. In fact, what they reckon is that the supernova may not account for the abundance of some of the heavier elements.
Yes.
We would expect them to be there, but not in the not in the volumes and concentrations we see them. Instead, they reckon a lot of them come from the collision of neutron stars. So as Jen was saying, if you get neutron star near another star, it can steal mass. But if you had two neutron stars next to each other, they can't do that. They're too dense. They don't tend to steal. So what happens is they orbit and they'll decay, and they'll slowly get closer, and then they'll collide. And I actually remember getting a talk from one of the they've actually now made like a pop art style cartoon of her. She's one of the amazing astrophysicists at University of Sydney. She was one of the 1,500 astronomers that first observed one of those events. And it was so it was also detected by LIGO, so it was gravitational waves. It wasn't the black holes one, this one came later. But it was the first time the gravitational waves was matched up with actual
astronomical
visual
observations. Yeah.
spots. We detected the gamma ray burst that came off them. I think it was only a couple of seconds difference. So they reckon that they just occurred at different parts, and that's why we had a time difference. They weren't in the same location they were coming from. But we actually matched the gravitational waves up to an observation. And because they had the gamma rays and the gravitational waves, they're able to roughly triangulate what part of the night sky it was coming from. So they went back through all the astronomic data that they were collecting from hundreds of telescopes all over the Earth, and kept cycling through them until they figured out, or tried to see if they could spot it, and they saw this collision occur. So it was the first time we actually matched gravitational waves up to actually seeing what happened. And it matched our predictions very closely, but they reckon that is where we actually get
the higher
our
elements.
heavier elements from, is that collision. The inside is too dense, we don't lose anything, but the stuff around the outsides, particularly on what would be roughly the poles, gets sprayed out into the universe.
And you're already talking about some of the most dense matter, because you're talking about neutron stars that's in the universe.
Oh,
So
yes.
actually the matter that we get afterwards is basically from that decaying. Because
yes, I'm talking, we're talking masses several times bigger than our sun, in a ball that would fit above Sydney, about 50 kilometers across. So it's essentially a sun that is smaller than a city.
Okay.
I think a teaspoon is like some ridiculous number of thousands of tons for a teaspoon of this stuff. It's essentially one giant atom. It's that dense.
It's a crazy.
But they give off a lot of energy when that happens, and they're the result. You get neutron stars, the result of a supernova. But if they're too dense, you end up them collapsing into a black hole. And there's a poster has a figure from a paper I've seen.
Yeah.
It had mapped out a lot of the known neutron stars that we've spotted, and the sizes of black holes, and it kind of has mass up the y-axis, and there's this giant gap in the middle
Yeah.
of this mass where we just haven't spotted things that heavy, and this collision would have brought those two neutron stars into that mass. So I always found that weird that we just hadn't spotted anything there.
But now we have.
But this is the sort of events that we need to create all these extra elements that might provide us life.
Yeah. We've had a couple of questions. So Nerdy's got one here. How realistic is astro mining in computer games, and would mining laser and scoop work well? Lasers are the worst way to try and mine anything. They're just so energy inefficient. If you wanted to mine, you'd be better off landing on the asteroid and digging it up with something more conventional.
Yeah, you'd be better off trying to capture it and probably bring it back into like Earth's orbit, maybe, and then you can take it from there.
Or land it on the moon or something.
In fact, that's one way they think you're making a space elevator. You'd capture an asteroid and have it like orbiting Earth, and then just tie like a rope to it, so the Earth would have a pet asteroid that goes around with it.
But we had a question from a Harmonica Man earlier that I did put up. Does gravity have an effect on our readings? If light is absorbed by differing strengths, wouldn't that mess with what comes back to us?
So I think what he's getting on is maybe gravitational lensing. So gravity does affect light, but in the same way a lens does. So it distorts, it changes the direction of light, can shift the wavelength, but these effects are very well known. We can predict them pretty much exactly. So in fact, when we see these things, we can tell whether they've had certain effects applied to them.
Yeah.
No, dog. That's something else. Just looking at the current question.
Yeah, that's why I thought I'd bring this one up. Because
yeah.
I'll answer it. I'll give you a break. So like the white dwarf is a stellar remnant that would come from a star about the same size as our sun. It's the leftover matter after the star throws off its outer shells, which is what a neutron star is similar. The difference is on very massive stars, when they throw off their outer shells, the internal pressure that pushes the core back together compresses a lot more matter together. So you get a neutron star when the star that dies is too big, is big enough to have a proper supernova, but not big enough to create a black hole. So a neutron star is basically a failed black hole.
Yes. And a white dwarf is a failed neutron star.
Is a failed neutron star. Well,
it's essentially
no, because white dwarfs
the
come out of
blown off a lot of its elements. It's run out of fuel. So I think the white dwarf is also a bit misleading. It's not actually a star because it's not producing energy.
It's actually more like a very, very heavy gas giant.
Yeah,
it's closer to that.
They're bright because they're still hot. In fact, the remnants are so hot that they will stay so for like a few million years at least, or more than that. Like the actual time scale it takes for a star to cool down is insane, even after it stopped running, like it stopped producing extra energy. I remember I'm trying to remember all the numbers. It was the notes I put up or showed up earlier. We actually calculated like some of these constants of the star, our sun actually, because we're using one solar mass, stopped.
Yeah.
How long would it take us to notice certain things? So how long would it take for it to cool down? How long would it take for certain radiation pressures to stop? The sun itself, if the core of our sun disappeared, just collapsed, say, into a black hole,
yes,
it would take 10 minutes before the outside of the star actually crumpled in, because it would take that far for the matter all pushing on each other to start falling in. It's like the ground falling under you. It'd have to fall from the bottom and eventually get to you. And the sun is just that big. It would take. So we wouldn't, like, the sun wouldn't know for about 10 minutes that its middle had gone. Then it would take about another 7 or 8 minutes before we would see it, because the light coming here, there's that delay. But if there's any residue heat that gets sprayed out, that's a different thing. But when you talk thermal timescales for astronomy, you tend to talk in millions of years. But if the inside collapsed to a black hole, temperature's gone.
And the thing is, even if that did happen, if you were in a star system and the core of your star collapsed into a black hole, And yeah, okay, eventually that would mean after so many minutes your star would go out. But it wouldn't change anything for any planets orbiting unless they were orbiting really close. So the outer planets would keep orbiting the black hole. What would eventually destroy the planets is that you'd end up with an accretion disk around that black hole, because the tidal forces close towards the black hole would start tearing nearby planets apart, and they would create in the disk around the black hole, which would create a lot of heat, and that is what would slowly tear all the planets apart. But initially it'd make absolutely zero difference. Spaghettification. But I mean, unless of course you cross the event horizon, that doesn't happen. So anything outside the event horizon just orbits as though it was orbiting a star or anything else that's massive. I mean, black holes are more dangerous because of their accretion disks than actually because they're black holes.
Actually, I want to have a go at Dog's recent comment about what would happen if we got... because I want to change it slightly to what would happen if we did get pulled in. In fact, you can get pulled into a black hole and survive.
Yes.
So it's not a death sentence if it's a big black hole. So if the black hole is... So smaller black holes actually give off more radiation. They're hotter because they have to give off a certain amount of energy. And the bigger they get, the larger the surface area, so they don't need to radiate as much per point. So they essentially get colder as they get bigger. So if you've got a really big black hole, the radiation won't kill you. And if it's big enough, you won't get spaghettified, which is a term for the gravitation pulling on you, the top of your body and the bottom, so assuming head and feet, but it doesn't really matter which way around you're orientated, is so different that it tears you to shreds, which is why a lot of depictions of black holes don't have planets orbiting them close. It'll be that, as Jen was talking about, that kind of like just a disk of destroyed material that floats around them.
There's even a possibility
if you don't have that,
you could have supermassive black holes, as long as things were orbiting, and stars do orbit supermassive black holes. You could have stars orbiting far enough out from supermassive black holes that those stars themselves could conceivably have planets around them still. And it would be a very extreme form of life, but you could technically have life on a planet orbiting a star that's orbiting a black hole. Technically.
Yep. The other thing too is that when astronomers have tried to, because with all of this, there's also a lot of people who try and do simulations for it. So because that's one way to try and check what's going on, because we can't see inside a star. So what we do is you'll run so many simulations to try and get the parameters correct. And when the outside parameters match what we actually see, it's not 100% proof, but it's a good indication that our understanding of what's going on is fairly correct. And so when they started coming up with all these simulations for these supernova that would leave all these remnants behind, so many of these simulations just failed. They just ended up with like nothing, or they ended up with a black hole, and the star never went supernova. And they, for a long time, were thinking, okay, we're failing. What are we doing wrong? Because this is not what we see. Then someone pointed out, wait a minute, what if our simulations are showing us something we haven't seen yet, but does happen? What if some stars just fail to go supernova and just collapse into a black hole? So essentially the star just disappears.
Yeah.
And they're like, and we know roughly how long the large stars last for. So you can figure out roughly how many of them you need to watch for how long before you would expect some of them to go supernova. And so they watched, and they started looking, and they found it. They actually found some stars that just disappeared.
Yep.
So they went from being emitting to probably a black hole. So it's also possible that, you could have that happen, where you just have the sun just disappear to a black hole, and the planets further out just keep
spinning,
orbiting.
Just keep spinning.
And as we were mentioning earlier...
You also have stars that, large stars that will do a more like a nova, like a star our size does, and then collapse their core. So they don't do a full supernova; they do a smaller nova, like our star will, and then the core collapses. And that's what they think happened with the Crab Nebula, because they've struggled to find the remnant, because they were thinking there'd be a neutron star or it'd be a white dwarf at the center, but they can't find it. their thinking is that it was a very large star that basically just did a nova with its outer core, but there was a lot of core, which is why the Crab Nebula is so big, and that the rest of the core just shrunk straight down into a black hole. So you didn't have the really big explosion; you had a smaller explosion and a black hole. So the star that actually created it was a lot larger than they thought it was, because they were looking for a star of a certain size, but it was actually something a bit bigger, and you end up with a black hole. There's a few different types of novas and supernovas that we are just learning now are things that can happen. And it's really extended our knowledge of the type of novas and things like that we can have out there.
Yeah, which is leads... And it's all linked. It's just showing us just how much we don't know about the universe. But I do want to point out that we are observing the universe from pretty much one single tiny point.
Oh, yes.
And look at what we figured out about how it works. We have figured a lot about how the universe works.
Well, we've done well talking about this without Tessa, and she's still not here. I'm guess she did actually say she was going to be held up getting here, so I don't know how long we're going to be talking for before she actually gets here. But that's the way it is. But as I said, we're taking your questions, and if you can support the channel, that would be awesome. It helps us do more and more stuff. So links are in the description for Matt's channel, for Tesla, and for my Patreon, and to follow me on Twitter. So go follow everything and help out if you can. There's no requirements, but it's all kind of cool. And I just wanted an opportunity to play some things. We've also got a new one, which I haven't used yet. And so I may as well show it because Matt hasn't seen it yet. So this is the new thing. So
I'm just seeing the Patreon one because of the delay for me. I've got the YouTube on the side.
So this is the new graphics.
It's going to take a few...
It'll take a couple of minutes before Matt sees it.
So yeah, you're just going to see me sitting here, and then all of a sudden I'll react. Oh, this one.
Yeah.
You were talking about that one earlier.
I was. So we've got our own little alien for the channel, because this is the second time Matt and I have talked about aliens and space travel and stuff like that. Although more formally in our show together this time than it was last time, where we just sort of got together and had a bit of fun because of something Matt had said in a chat. And I stole his idea.
Yes, that first stream was, but I don't mind that. But I am trying to turn some of what we're talking today into a proper video when we're going to record.
I know you've got lots of questions to ask Tessa when she gets here to help with that. If she doesn't make it here on time, but I know she said she was going to be held up a bit, and we thought we'd just cover until she got here. If she does get held up and doesn't make it for tonight, I will try and rebook her, maybe for next week or the week after, and we will get to talk to her, because I really, really, really want to talk to her. Talking to an astrobiologist is just so cool. Matt and I can give you some ideas of things because we have a genuine interest. But this is now Fields, and talking to somebody whose it is just going to be so much better. So yes. I still want to talk to her.
I've also surprised it took this long for the chat to devolve into the current topic it's talking about.
Yeah, well, that's Dave's fault because he joined the chat and started licking people.
You can lick the subscribe button, but
yeah, lick the
make
subscribe
sure you
button, and don't forget to click the thumbs up if you haven't already, and all that. So yeah.
We got an extra thumbs up.
Yeah. So yeah.
Unfortunately, you can't lick neutron stars.
No, your tongue might stick. Than the rest of you, and they're also really, really, really hot, so you'd melt.
Yes, they're quite warm. They're left over of a star. I think it was
a dog who brought up earlier that neutron stars are so heavily compressed that you no longer have what we would consider normal matter for us. You end up with this strange substance called quark matter, which is basically the quite the constituting parts of ordinary matter. And this will be covered better later on when we actually talk to a particle physicist. But because this also is Matt's on my field, but so the star is so heavily compressed that you now no longer have just compressed hydrogen or helium. You've actually got matter that's gone back down to being just the quarks that make up so you've got a star that's made of baryonic matter, basically. So, well, I mean, everything's made up about. What am I going on about? Everything, but you're going back to your basic constituents of matter instead of actually having the elements that we know.
Yeah, I as I was saying.
Oh,
earlier,
and we've got Tessa in the background. Hi, Tessa.
Hello. Sorry for being a bit late, but
That's
I made it.
fine. That's
Yes,
fine.
Lynn.
We've been filling in for you, and I'll get you on the screen where people can see you. So that should be working. I will just click back and make sure people can see. They can see you. Brilliant. Thank you, Tesla, for joining us. We've had a heap of questions from the audience here. But tell us a bit about yourself, Tessa, because you do a podcast. You're an astrobiologist,
Yes.
which I think is fascinating. So tell us a bit about you and what you do, and where you're studying at the moment. Because you're PhD. You're studying for your PhD, a bit like Matt is.
Yeah.
So, yeah.
Yeah. So my name is Tessa Fisher. I am a PhD candidate at Arizona State University in the School of Earth and Space Exploration. And I'm an astrobiologist. So looking for life beyond Earth, trying to figure out how it might have evolved here and elsewhere in the universe and how it might continue to evolve. My area of expertise, sort of what I'm doing my dissertation on, is using a branch of mathematics called network theory to hopefully try to develop better ways of detecting if there's a biosphere on an exoplanet, so a planet orbiting another star, based off of its atmospheric composition.
So you must be really excited about James Webb launching later this year.
Oh yeah, James Webb and the other possible follow-on of LUVOIR, which is an even bigger telescope, are pretty much what my research is hopefully designed to work with once those telescopes are up and running and we have some data from them. Hopefully.
Yeah, because it's such a thin portion, like a thin slither of the night sky that we're actually looking at, because it's not the whole atmosphere, it's just the tiny bits that stick on the outside of the planet, isn't it?
Exactly. Yeah, so, we're dealing with a lot of uncertainty inherent in the data, and it's not a lot to work with, and we've got to make a lot of really powerful assumptions from that data. So, anything we can do to, get a better, feel and a better sense of certainty about it is going to help.
Awesome.
Yeah, so my area of study at the moment is spectroscopy. I deal with gas detectors and probably for environmental monitoring, but there's been talk in the group, because I'm technically part of an astrophotonics group, of trying to be able to see through the atmosphere and infrared so that we can do similar things, but with ground-based telescopes.
Oh, yeah, that would make sense.
But yeah, I'm just thinking, so do you know what kind of resolution we'd need to spot this?
That is actually something we are hoping to figure out eventually. Right now, we're just trying to prove if this very abstract mathematical method even works.
I see a collab
and once we do that, once we figure that out, it's going to be okay, so if this works, how big of a mirror on our telescope do we need to get the high resolution spectroscopy data? How many different molecules in the atmosphere do we need to identify in order for this technique to work, etc.? So that that's further down the road, but that is something we're hoping to determine.
Are there any particular chemical signals that you're looking for, or is the whole idea of this mapping to try and figure them out?
Actually, we are specifically not going for that approach, because for a long time in astrobiology, the assumption was, we just look for oxygen because plants make oxygen. So if we find oxygen, that means there must be life there. And it turns out, as we've discovered, there's a much greater diversity of worlds than we originally thought, and also, we've gotten a lot better at modeling and understanding the sort of development and evolution of planets over time. We've discovered there's actually a number of ways you can get a very oxygen-rich atmosphere that have absolutely nothing at all to do with the presence of life. So, there's a huge risk for false positives. So what we're hoping to do is that instead of looking for a particular, kind of smoking gun molecule, whether it's oxygen or methane or DSMO or whatever, that instead we are looking at sort of the statistical pattern of interactions between the different molecules in the atmosphere, hoping that that's where we might find, signs of life. And if it works, that will avoid hopefully false positives problem. And also, since this is kind of based on the assumption that there may be sort of like universal laws of life, that just due to the laws of physics, biology everywhere, no matter what molecule it's using as its base, if it's carbon, if it's silicon, if it's using water, or if it's using ammonia, it will have certain patterns emerge, in its chemical interactions, and that those will show up in turn in the atmosphere that it interfaces with.
Wow.
There's a lot.
That's all I can say.
See,
that's
I'm
so
used
much to observe.
looking for single chemicals because that's what my PhD is in.
Right,
so how far
right.
through your PhD are you?
I am in my 5th year. I am hopefully going to be finishing, knock on wood, in no later than spring of 2022. So I am hopefully almost out.
So have you started writing thesis then?
I have a very nice literature review chapter, and I have a paper that's currently in review for Astronomical Journal. That's probably going to be like chapter 1. I just started like what's going to be the next chapter, like earlier this weekend actually. And my code's not working, and I got to email the guy who maintains the code to find out why it's not doing what it's supposed to do. But hopefully, I will have results for that relatively soon.
It's not coding if there aren't bugs with it.
Oh yeah. It's kind of like, okay, a lot of it is atmosphere modeling for obvious reasons, and it's like, okay, I just like increased the carbon dioxide levels to like by 200%. Why are my model results the same as when I didn't do that? What, Okay, clearly something is not being communicated here. How do I fix this?
What programming language do you normally use
Python.
for that?
Python, although the technically right now the modeling software I'm using is a Python wrapper around something written in Fortran, which is just tons of fun.
Hey, what? But you're still using Fortran?
That's all.
Oh yeah. NASA just loves Fortran. Partially, it's like it does have some advantages in that it's
Formula
really
translation.
You can do, like,
but yeah,
that, and you can do ridiculous like optimization stuff with it. But partially, it's also just sheer inertia.
Yeah. Yeah, because NASA's this beast that's been around for so long now that they just can't change.
I have literally in the past worked with like code for atmospheric modeling, not this one, but like another one, where like in like the comments section there were still legitimate references to punch cards. That's how like old the base was.
Oh,
and I mean,
wow.
I thought it was old because I've used a floppy disk.
It had been adapted and modified since then, but people had kept those notes. For posterity's sake, and it's just like, wow, this is ancient.
Damn.
Damn.
That blows my mind. And I've got a computer science degree. So
I had a friend who was talking about bugs with Python. They kept wondering why their code like some of their values kept moving, and they set all their initial parameters to 0 to figure out why their numbers weren't matching. And if everything was 0, nothing should change.
Right.
But yet something was changing. Turns out because of they were using like single letter variables, but in Python you write loops by easily going for. Yeah. And then you write a new variable in this. So if you go for r in say x, then for however many values are x, it'll take a single point, and r will be that for each one. So if it's 1, 2, 3, r will be 1, then it'll be 2. And so that they'd accidentally done that and rewritten over one of the variables.
Oh no, like I've done that before. Yeah, you got to be tricky. You got to be careful with it. It can be tricky.
Doug has a question I'm not a coder. For us, and I think it's an easy one to answer. But Tessa, would it be worth sending a probe out to one of these planets, even though we ourselves wouldn't see the results?
Yeah. I mean, like, it's a little hard to imagine the timescales, but, if you think about it, science as like a multi-generation endeavor, and there's precedent for this. I mean, the standby example is that the great cathedrals of Europe, it took them in the Middle Ages like hundreds of years to build, so the people who started them would never see them completed. So yeah, in that respect, it would definitely be worth it, even though the people launching it wouldn't necessarily be the people who got the results. But, it's that long-term thinking is the only real way to do that type of like hardcore science of actually sending a mission there.
But we've got
the engineering challenge is be something else.
We have missions like that now because I mean, a lot of the people who originally worked on Voyager are no longer with us. So even with our they saw some of it, but not all of the results of Voyager. So.
No, it's totally worth it because, like, I mean, again, this is like long-term, generations-long science.
Of course, the one problem we would have with the technology we have now, is we have no way of powering a probe for that long amount of time to get.
I mean, there are, like, if you just had like a big honking nuclear reactor on it, you could probably do it with well designed for like probably about 100 years. But like no one's built one of those for space yet, I don't think. So like, like again, scientifically, there's no reason you couldn't do it. But the engineering hasn't been done yet, which is a non-trivial obstacle.
Oh yeah, the engineering is immense.
Yeah. Some of the longest spaceships that I've heard of that, like, say aren't. I mean, because even solar panels degrade over time.
They degrade over time.
And that's the problem. It's not that you can't find more light. It's that the panels die and you can't recharge. I mean, that's happened with some of the probes on Mars already.
Yeah.
The longest I've heard for actual spaceship designs in any project is, as you were saying, about 100 years, I think. There was a really crazy idea that Freeman Dyson had towards the end of his career, was you could potentially do a generational ship to Alpha Centauri in 100 years or just under 100 years if you powered it with nuclear bombs.
Project Orion. Yeah.
The
crazy thing about Project Orion is that it gets like the drive of just like propelling it with atomic bombs. I don't know the math on this, but apparently it actually gets more efficient the bigger you get. So you end up scaling this thing that's like literally a million tons. It's the size of a small city. And
one of the spaceships they planned as part of the original Project Orion was going to be powered by hydrogen bombs, like 60 to 100 kiloton hydrogen bombs, which is small for a hydrogen bomb, or maybe that was the nukes for the smaller ones. But the actual rocket ship itself was meant to be the size of the Empire State Building.
Yep, sounds about right.
Yeah. And like solid steel, and they did test with conventional explosives, and it looked like it would work. But if we wanted to move
it totally would work.
It was they didn't know whether the plate would survive the nuclear blast because they never got around to testing.
Yeah, they have pretty good evidence that it probably would, because when they were doing one of the underground tests, they accidentally shot the top off of it, and apparently it survived. It very quickly afterwards vaporized in the atmosphere because it was basically ejected at escape velocity. But it survived the initial explosion. And the other thing they were planning on doing is basically they'd have sprayers built into the plate that would shoot a layer of oil across it right before detonation, so that would absorb a lot of the heat and not burn the plate.
Oil protects from nukes.
Yeah. We've had a statement more so than a question about solar sails, because saying they'd work and we could send. We know solar sails work. Which is fine, but you're actually better off building a very large laser at this end and actually shooting the laser out at them, relying on solar energy, because it doesn't.
If you're talking about interstellar, yes, because the amount of light energy you get from the sun falls off
at a lot
inverse
square rate. At
a pretty fast rate,
because it's surface area, so it'll be 1 over r or d squared. The thing I have with that is that the laser will also
spread
diverge.
Out,
and the laser slowly ablates whatever surface you're using to reflect the laser off of as well. So you're actually decreasing with efficiency the longer the ship's flying as well. Not just because of how far away it is, but because the laser actually affects the surface that's reflected.
It's meant to be efficient. My problem is, how far you'd go before we just can't focus a beam that far.
And then you have the bigger problem. Project Starshot is a great idea. We could conceivably build a laser large enough, or an array of lasers large enough. We could conceivably build the solar sail. We've tested these things. We know they work. But even if you do that, you can only send a really tiny probe.
Yeah, it's literally the size of a cell phone.
Yeah, and you can't slow it down when you get to the other end. So it is literally a starshot. It just flies straight through the solar system and out the other end. And you got to hope that something goes close to what you want to see.
Yeah. Basically, you have to figure out a way to do meaningful science at an appreciable fraction of the speed of light with a probe, again, the size of a cell phone.
Yeah, and get that
yes.
signal back here because it's not going to have much power once it gets there.
Exactly. So,
and we already have a problem with low-powered signals in that the actual noise that's in interstellar space tends to drown them out.
Oh, yeah, yeah.
So we are pretty much in the shell within the heliosphere of our sun. There's actually less noise than there is outside of it, which we've discovered thanks to Voyager. So,
but yeah, I don't I don't envy the engineers who are looking at Project Starshot because
it's not insurmountable, but it's crazy engineering. It really is.
So on that. Oh, sorry. I was just going to ask a question about the noise because, like, my experience when I've been to some of the telescopes, the radio ones, some of the light ones, particularly the radio ones, like like the signals they're trying to detect through the atmosphere are so weak by the time they get here already that if someone connects to Wi-Fi or turns on like the data roaming on their phone, they detect it on the grounds. They detect it in the signals.
Two anecdotes for that. First of all, the one major radio telescope I've been to is the one up in Green Bank in West Virginia, and they don't even allow like digital cameras within like 500 yards of the telescope. You have to use like an old-fashioned film analog camera because the noise even from like the internal electronics of the digital camera is enough to like mess with the signals. And the reason you have to be careful about that is that a while back in another radio telescope, I don't remember which one, this was like decades ago, they found this really weird like infrared this like repeating astronomical phenomenon in the sort of lower frequency range, and it like only showed up at certain times of day, and it was always in different areas of the sky. I know
where this is going.
And they were like, this is really weird. Is this some sort of weird astrophysical phenomenon we've just never noticed before? Until they realized it always happened around lunchtime. And it turned out it was the signal from the microwave in the break room.
To that telescope. That's the one in Australia at Parkes.
That's Parkes.
And I've spoken to some of those engineers. So essentially, so it was lunchtime as you were getting to, but it was the microwaves when they opened the microwaves because they're old-fashioned microwaves. They're now not allowed to have microwaves there. But the engineers, when one of the guys was talking to us about it, was so proud of how they figured it out because they said it was a great example of science because it was process of elimination. They went through and tried to figure out what it was, and as you were saying, this was lunchtime. But it turns out this signal was just coming from the tea room. But it was a great example. But I've met some of the people for that, and they published several like papers on it, talking about these nice big features in astronomy, and they could tell they were local to this galaxy. They could tell they were somewhat local. It turns out they were far more local.
Yeah, they were local to the entire.
They actually built.
Facility.
So this is just a giant radio telescope. Instead of being an array or like a bunch of them, it's just a giant single one. It's the one that received the moon landings. And there's the movie about it. And they took us outside. That when they were detecting those, they actually built a second small one. It's only maybe 2 or 3 meters across the actual dish, which is quite small for a radio telescope. That's just kind of looking up into the sky generally to spot those. So they actually built an extra mini telescope just to look for them. And then it was like, then we kind of figured out that
it was us. We did it.
But it turns out they can use them for another feature that comes from outside our galaxy that we still haven't figured out. And it was very similar. It's just these giant spectral blips that were the microwave. But apparently it was the wrong frequency. That's why they didn't pick it up initially. It was the wrong... It was actually, they think, some weird phenomenon when they opened the door and the microwave was shutting down and the power was changing. That it actually shifted it to a longer wavelength.
That would do it,
which is why no one initially thought microwaves. I still like the idea of them.
It is awesome.
They're like, nope, it's just lunch.
I've got a question, Tessa. Matt's actually doing a documentary-style video at the moment about possible life within our own solar system. But Do you get excited about the about different exploration projects that they're going to do within our own solar system?
As yes, absolutely.
Yeah.
Nowadays I mostly work on other solar systems, but I did my master's thesis on Mars, and specifically sort of like modeling what a microbial ecosystem like underneath the Martian polar cap might look like.
Oh wow!
Based off of some subglacial ecosystems in Antarctica, including one that had been isolated from the rest of the world for probably about 3 million years,
which they have now discovered life in.
Yes. Several of them actually. The one I did on was Blood Falls, which is Google it. It's amazing. Yeah. But they've also done.
I'm making a note.
Lake Vostok.
He's making notes.
But yeah, so I think it's really exciting because obviously that's going to be much easier to do than detecting life on planets around other stars. And the really exciting thing is going to be is if we're able to detect it and even get samples of it, is determine if it has a similar biochemistry as our planet or if it's very different. Because if it's similar to ours, it's a possibility that, meteorites getting splashed off of a planet and then, drifting around in space for, say, a few million years and then landing somewhere else, you could potentially, seed life back and forth throughout the solar system
There's even a possibility that life seeded throughout our entire galaxy in that way. And we may not find any life that's different in our... Yeah, a lot longer term, but there's possible that all life in our galaxy could be DNA and RNA based.
Yeah. And that's one of the unanswered questions is that what we should expect or not? But the reason is if it's radically different, if that's what we find would be really exciting, is because that would suggest that the formation of life, which is something we have some better ideas how it might have happened, but there's still a lot unknown. One of the things we don't know is how easy is it to do that? Is it just a freak event, or is it relatively easy to do? And if we find that life has originated, 2 or more times completely independently in our own solar system, then it suggests it's a very high probability event, which obviously has a lot of really exciting implications.
Yeah.
Our galaxy may be teeming with life if that's the case, but we won't know that until we're able to detect, life in our solar system.
My gut feeling is life is probably ubiquitous. It's probably everywhere. But intelligent life probably less so.
Yeah, because one of the reasons people suggest it's probably common is that it pretty much, we can find fossil evidence of it on Earth pretty much as soon as conditions were hospitable for it. So it suggests it didn't.
Didn't they even find evidence that it might have been before we originally thought it was hospitable during the Hadean?
The Hadean era. There's some debate about that. But still,
because we don't have any rocks.
Yeah,
at all. It's
but
just
still,
zircon.
Very early in Earth's history. Which suggests it's relatively easy to get there. We don't know for sure. It still could have been a low probability event, but still it suggests that it probably wasn't. As for intelligent life, that's the tough part because you need to get to multicellular life. We think in order to sustain that.
We were a long time on.
It took a billion years on this planet.
To go from single cell to multi-cell, and then from multi-cells to anything that remotely could be considered intelligent took hundreds of thousands of years on top of that.
It took us nearly 4 billion years to get to complex life.
So I wouldn't be surprised if that's if you're looking for someone outside in the galaxy, out there in the galaxy that you want to talk to, I wouldn't be surprised if that's kind of one of the limiting factors. Is it just
that is probably the great filter more than anything else, is that evolution doesn't tend towards complex life. It tends towards microbial because it's hardy and survives, and it
But for me, that's one of the reasons I would agree with Jen that it's probably really common is that you can find simple life, bacteria-like cells almost all over Earth in all environments.
A kilometer down under the surface on this planet, you can still find life.
So it does look like these chemical processes might be far more common, but so I guess on that topic, where then would you say you think is more likely in our own solar system that we might at least first find evidence?
A good question. I don't know. the two top places I would look is that, as cliche as it is, probably Mars, because we do have those periodic like methane plumes on Mars that we still don't necessarily have a good explanation for. And, on Earth, pretty much all the methane we detect comes from biological processes. There are like non-biological processes that can produce it. There's a geological process called serpentization that can also produce it. But even that requires liquid water. So, it still makes you, there's still a lot of exciting implications if that's where the methane's coming from. So, I think that's definitely worth investigating. If there is life on Mars, I'm pretty sure it's probably like well below the surface. Like Jen was saying earlier, on Earth,
microbial. Yeah.
But we do have evidence for flowing water potentially under the surface, which would match with what you were saying.
Exactly. Yeah. So, either way, if we've got liquid water, that's also a good place to look. The other places that would be exciting to look are probably like the icy moons. Europa around Jupiter, covered by an icy shell. We know dead certain that it has a massive ocean underneath, larger than any on Earth. Although I have seen arguments about whether or not there'd be like enough energy available just underneath the surface.
Also, we also know it's probably incredibly saline, which could
which isn't necessarily an obstacle, because we do have stuff that lives under extremely salty conditions here on Earth, but it is a deterrent. It is an obstacle that life would have to overcome. Enceladus around Saturn, similar situation.
Plus, we've seen the building blocks of life in its plumes, because we've seen amino acids there.
Yeah, although one of my lab mates did an analysis of that, and he said it would be there may not be quite enough diversity of organic compounds, but not to like.
I think it's exciting just to get the organic compounds.
Yeah,
because that's the other thing you see. Even in gas clouds that you get in nebula, you can see the organic compounds.
Oh yeah.
So they're there, which might at least suggest in all places. So,
which I guess would reinforce that idea that it may not be that hard to get life. That some of the conditions are easier to meet than we thought. But that was an interesting point on. Yeah, not enough diversity. Do we have some idea of like, I guess this is what you're working on, the kind of diversity in chemistry that we would need?
Yeah, that's what we're trying to figure out. It's been like he graduated 2 years ago, and I'm trying to remember from his dissertation defense. But basically, like there is like a minimal seed set you need in order to like, and the analysis he did was really simple. It's like, okay, let's start off with very, very basic components. And what reactions are possible under the given thermodynamic conditions? How large of a range of organic molecules and building blocks can you make? And I don't remember exactly like how big like the minimal seed set for Earth was, but yeah, I remember part of it though was he was like, we shouldn't be too worried about contaminating Enceladus because it's unlikely that our life would be able to sustain itself there because it doesn't have everything our life would need. So but still, it's worth investigating.
But that doesn't mean we know everything that is needed for life, because life can be formed in different ways. Because we're still there's still a possibility there could be some sort of methane-based life on Titan.
Yes, that's another cool place that's definitely worth looking towards, which would be really exciting because that would be radically different. And they are sending a mission, Dragonfly, which is literally like a helicopter drone that's going to fly around Titan.
Well, it's also unlikely that if you've got methane life that the base building blocks will be carbon, because...
Oh, no, it would be, but not carbon as we know it.
Not carbon as we know it.
Yeah, because methane is an organic compound.
It is, yes.
But nitrogen would play a much, much bigger role structurally compared to what we see on Earth.
Yeah, so we wouldn't have DNA.
This is how the chemistry works.
DNA couldn't be made the same way because
it would not be DNA. It would be something.
In which case, if we find life on Titan, then we actually have found life that has evolved completely separately.
Yes. Yeah. So that would be a very exciting finding. Yeah. So those are probably like my top 3 or 4. There's been a lot of excitement about Venus. Initially, I was like really in favor of it. With the detection of phosphine on Venus.
We discussed that earlier.
Yeah, however, like the major obstacles you run into is that, while the upper atmosphere of Venus is like shockingly Earth-like, in terms of temperature and pressure, within, a broad approximation, certainly compared to the surface, you've got very little water, and it is really acidic. I mean, like, incredibly acidic.
Almost entirely sulfuric acid or other acid.
Yeah. People, it wouldn't be like water with a little bit of sulfuric acid in it, which is what you see on Earth. It would be sulfuric acid with a little bit of water in it. And so,
yes, and sulfuric acid does tend to gobble water up.
Yeah.
I can remember what would happen if you ended up mixing a bit of water in with concentrated sulfuric acid.
We actually covered this last week, Matt.
So anyways, I guess that's not necessarily insurmountable for life, but it does make it very, very difficult. And, just like last week, or actually earlier this week, a paper came out that suggested, the phosphine they're detecting may have come from volcanic eruptions in chemistry.
Yes.
It may be a false positive. But
I might, if you know that, I'll have to look for that publication. So I got up to, I was doing Venus today. I was looking at it for the video I want to make on it. And yeah, it also looks like they may have made an error in the background measurement so that the detection limit is much lower.
Very controversial because people are like, yeah, because on one hand, it's possible that it was just background noise. On the other hand, there's some data from one of the Pioneer probes that they sent back in the 70s and 80s that may also suggest phosphine was detected. It's one of those things where we're probably really not going to know without further measurements. But even if it is there, it turns out there are other ways you could make it that don't involve biology. And I'm seeing if I can find the link.
Yeah, because I was trying to get through it today, and it was just papers going back and forward, and people going back and forward, and it's like.
And I mean,
but it looks like it's probably not as significant as originally thought, but it's not been ruled out. That's my understanding. Is that correct?
Yeah, exactly. And it's interesting watching this happen because the exact same thing happened about 10 years ago with detection of methane on Mars. Because until I think Curiosity, we didn't have solid confirmation that there was methane on Mars or not. And it was all from remote observation, and it went back and forth for a couple of years of, well, no, you're just getting, since they're observing from Earth, this is just contamination from Earth's atmosphere. Well, no, because it fluctuates. What we're seeing on Mars fluctuates seasonally based on the Martian seasons, which suggests it's happening on Mars and not on Earth, because on Earth it would be constant. It basically was, quite the debate going on for a couple of years, and it wasn't until Curiosity landed and confirmed, a year into its mission, that no, there actually is methane here, that it was finally settled.
Oh wow!
Yes,
so
but because sorry, Jen.
Oh no, sorry, I was just wowing because it took that long. No, go on, Matt.
I was gonna say, but see, at least with Mars is easy to put probes on than Venus, even though Venus is closer. The problem is that probes don't tend to last very long because, as you were mentioning, the atmosphere is pretty much sulfuric acid. And I was looking today at some of the other acids. You get hydrochloric acid as well, and hydrofluoric acid, which will eat through pretty much everything.
Yep.
If anyone remembers, if anyone in the chat is what was watching last week, that's the one that'll get inside your bones and eat you from the inside out.
Yep.
And we've detected parts of it. And it's also, yes, as you were saying, the upper atmosphere has temperatures and pressures similar to Earth, but the lower atmosphere is about the same as being a kilometer under the ocean in terms of pressure.
Yep.
And it's 800? No, about 500 degrees Celsius.
Yep, it's hot enough to melt lead. Yeah,
and there's virtually no free oxygen there at all. So
no, it's almost all entirely carbon dioxide dominated.
Yeah, so any form of respiration cannot use any oxygen.
Yeah, which I mean, that in itself isn't necessarily an obstacle.
No, it isn't.
We didn't have oxygen on Earth for the first billion years, and there's plenty of life there. The other factors involved make it a hard sell. Although I did have another collaborator within my lab who pointed out that theoretically on Venus you could get supercritical carbon dioxide as a fluid, and that actually apparently is better at some organic and biological reactions than water is. It's still a bit of a stretch, but it was definitely interesting to think about.
Yeah, because but my favorite story about trying to land probes, because the Russians have done it a few times, but they had to try so many times to get it to work.
Oh yeah.
But one of my favorite stories, they were the first. It was the first time we ever got photos of another planet, the surface of another planet was Venus, and it was done by the Russians in, I think it was 1975, if I remember correctly.
Sounds right.
But,
Right that, yeah.
But one of the probes, they sent a number of them, and the first two that actually made it safely to the surface.
Weren't they the Vostok probes? Is that
Yeah,
right?
yeah, something like that. It's
Yeah,
something,
something
Venera.
like that. Oh, the
Venera.
Russian stuff's
Yeah,
going to
yeah.
get us again, Matt.
yeah, and the first one could only get 180 degrees. It was meant to do 360, but one of the lens caps didn't come off. 2 or 3 days later, the second one landed and had the exact same problem.
Wow.
They then landed number 14. 14 is my favorite. They had a little probe that was going to detect what the surface was like. So it was just a little like needle on like an arm, and it comes off and goes whack onto the ground. And it tells you how hard the ground is or soft. And so you can get some idea of what its kind of composition is.
Mm-hmm.
And as I said, they were using lens caps because you couldn't just have the glass go through the atmosphere.
Right.
You'd die. So you had to pop the lens cap, pops off, lands, and then the arm comes straight down onto the lens cap.
Yeah. Apparently, like the analysis people got really weird results. It's like, why are there so many like hydrocarbons on Venus? This makes no sense. And I'm like, oh, it's the plastic from the lens cap.
Yeah, it's a good example of Murphy's Law. If there is a way something could go wrong,
You can go wrong.
that was sorry, but they managed. I think the longest they could keep a probe alive was 2 hours before the
about
temperature
that.
and pressure.
There
think
were
got
two
to it,
other
so-
potential places that Matt and I were talking about earlier. One was the fact that they discovered that there's areas on Pluto where they think they're under some of the fluid underneath has been melting by the gravitational interactions of between
With
Pluto and its
the moon,
moons.
Chiron. Yeah.
Yeah.
Mark Navu, who is a grad of my program, like did his dissertation on that, like looking for oceans underneath Pluto, and it's. I think what he found is it also depended on where Pluto was in its orbit, but still, it's definitely kind of like worth thinking about and like examining because Pluto could have oceans on it.
And given what we know about tardigrades and smaller microbial life, even if they're only oceans for a couple of hundred years of its orbit, and then the rest they're frozen, that life could still survive and then be okay in the next come around and just
thaw out and keep
going.
Pick
So
up where you left off. Yeah,
it's conceivable we could have life even
There's
out as
plenty
far
of
as
life
Pluto.
on Earth that does that.
yeah.
And,
Most bacteria, I think you can do that. They freeze and then
A
you
lot
can
of
melt
them, yeah, you can.
and the other one that I
so-
said, Matt, was Mercury, because there's signs that we could have liquid water in some of the craters at the equator. Not the
Not
equator,
just
at the
Mercury.
poles, sorry. At the poles.
Yeah, so the craters might be enough to shade water in there so it doesn't reach the searing temperatures that the sun side does. Well, I mean, because it rotates, but if you're at the poles and you're in a crater,
you're
it doesn't
always in
matter if it
darkness.
rotates. And they found evidence that there has been volatiles that have like evaporated and come off the surface to leave certain debris and features on it that weren't previously explained by like just impacts or maybe very early tectonic activity. It looks like these occurred potentially astronomically recently as well.
Yeah, I mean, tens of thousands of years, but
yeah,
Still.
and it does look like that some of the gases, even though it doesn't really have much of an atmosphere, it might be enough that some of them, if they do get boiled, will then move around to the colder side and then freeze again into the ground, and so it could accumulate chemicals. And another one that she mentioned, I was listening to one that Jen sent it to me as one of the scientists who had the paper was talking about it, mentioned that they did also detect a lot of sulfur dioxide as well, might be the other one. And I mean, sulfur's been detected pretty much throughout a lot of
you're going to
these
have to
planets
send
that we're
Tess the
talking
paper
about.
later now.
Yeah, I'm very intrigued by this. This was one I had.
Yeah. I can get the link. I've got it up. I've got like a million tabs on my other screen because I'm just going through. Well, I'm trying to do it one planetary body at a time, but even still, it doesn't take long before it's like.
Yeah. Oh no, I can imagine. I can imagine.
And then,
I think
course,
it'll be more.
On top of that, we've got that the spot that we saw in series when the probe was there. And they've discovered,
haven't got to that one.
Well, they've discovered that it seems to be acting like a geyser. So if you've got a geyser, that means you've got liquid under the surface.
Yeah, or some form or another.
Fairly recently, recent enough so that you've still got the stains on Ceres. So I mean, potentially another place in our solar system that could have the building blocks of life. I mean. We're kind of hopeful in a sense that we will find something this close, because this close is exciting to us because it's easy. We can get there, we can reach it, and we're within people's lifetimes. Even if it's Pluto, we can do it in somebody's lifetime. So
right,
which is better than further out. But I mean, we've talked about the solar system, but I mean, your stuff is to do with beyond that. What you'll be able to see with James Webb and the telescopes beyond James Webb. What currently discovered systems excite you the most? Do you really want to get Webb aimed at to try and see what you can see?
There are a couple like Kepler system that the Kepler telescope detected that are exciting, and also the more recent TESS mission as well, where we're still kind of like we'll need more data to really like kind of narrow down what type of planet we're looking at, but they look like fairly Earth-like planets, sort of in the right distance from the sun that they could have liquid water on them. So that's exciting. Yeah. And I mean, like, there's still debate about that. Like the TRAPPIST-1 system, which is another system that got a lot of press because it has like 7 planets in it. There's been a big debate about how habitable those planets may or may not be, depending on their mass. Okay,
and
based off their mass,
how flary the star is, etc.
Yeah, that too.
Because you've got the same problems with Proxima Centauri in that sense, haven't you?
Yep.
Because we've got this nearby planet that's about the right size in the habitable zone, and a star that's throwing flares out weekly,
like on a monthly basis. Yeah.
It's got really bad period pains.
Yeah, no kidding. Like. It's a bit harder to put like limits or constraints on, okay, how likely do we think there's going to be life there or not? But still, the fact that there's so many planets to choose from, some of them have got to be winners. So I'm looking forward to, as James Webb, hopefully gets into orbit and we have more data to look from, we'll be able to have a better feel for how habitable these planets actually are. So there are a couple of those planetary systems. I can never remember the names because they're just like number sequences.
They're arguing in the chat about whether Pluto's a planet.
I'm not even going to get into that one.
Yeah, no.
And there's another system which is probably not aliens, but it's still really weird, called Przewalski's star, which is a very hot, relatively old star as these things go, and it's noticeable because we were talking about spectroscopy earlier. You can use spectroscopy to determine like what the composition of the star is, as well as the composition of an atmosphere, and it's got like a bunch of signatures for like heavy radioactive elements like uranium and thorium in it. And well, the current explanation is that there's some really weird nuclear physics going on, that there's like these metastable, super heavy elements that we haven't even been able to like manufacture on Earth there, that are decaying into like uranium and plutonium, and that's why we're detecting it. It has been pointed out that you would see the exact same signature if a civilization was dumping its radioactive waste into its host star. So,
which is something
weird's going on there. Yeah, theoretically.
Yeah. Although to be honest, it's really hard to dump something into a star. Orbital mechanics does not help you at all.
No. Like, it would, like, pretty much, if you're doing it deliberately so other civilizations can detect you there. It would not be a very efficient way of, like, getting rid of your waste.
You'd be much better off finding somewhere in an asteroid belt or somewhere like that to take your waste away
or just,
from
it's just actually easier just to eject it from the solar system entirely if that's something you're worried about. But yeah, so that, that's a weird thing going on that I hope they're able to figure out what the situation is with that.
So I had a bit of a question. So could it possibly be remnants from some older star? Is that something that they can rule out here? Because that's the first thing that came to my mind, but I'm not familiar.
Not sure. If that were the case, I think the suspicion is we'd see it more frequently, but I don't know. I'm not a stellar physicist, so I don't know like whether or not that would be precluded or not. Because this is like a very rare find.
I mean, we have finds in astronomy where we've had white dwarfs orbiting within the corona of a larger star. So is it conceivable that we could have a dense remnant?
It's possible. Yeah, you could have like a stellar remnant in there.
Yeah.
Although I think we've gotten pretty good at detecting those. Again, I'm not a stellar physicist.
They cause lots of wobbles within the star, I would assume.
Yeah, like they'd cause irregularities that you'd be able to pick up. But I mean, that could certainly be a contributing factor. Again, it's not really, narrowed down what could be causing that.
This is probably questions we should save when we've got the astrophysicists on. No. This one.
Yeah. I mean, but on this, I think a lot of this just seems to be like our resolution is always the issue. But like as I said earlier, the group I'm in is working on ways to do better astronomy from the ground, not necessarily satellites. Although there are members of the research group that work on CubeSats, so mini tiny little satellites. But one of the methods that we're looking at potentially down the track could be used to background out most of the infrared absorption our atmosphere has. So we'd be able to see from the ground, or be able to, if you can background it out, turn it fairly invisible, and you'd be able to look towards these other planets. And another one was adaptive optics, where you have like a wobbling lens that corrects for atmospheric distortion. And like some of those, like if we could do that, then we could just build like larger telescopes from Earth. Do you think then we would still need some of the orbiting telescopes?
Like, that would make life a lot easier. I mean, like ground-based observatories of that scope are still like not trivial to build, and they're still rather expensive. But on the other hand, you don't have to have as many limits on the size, just because you don't have to worry about cramming it into a rocket and then shooting it into space. So I think there's still going to be some demand for orbital observatories, especially in wavelengths that tend to get absorbed by our atmosphere. Like, it would be very hard to do ultraviolet in some frequencies from Earth because, the ozone layer absorbs most of that. But for visual and for other frequencies that are transparent to the atmosphere, you could actually see sort of ground-based observatories taking the lead.
Well, this is what I was getting at. Some of the technology that the group works with, and I wish I could say more, but I got to be careful because
right.
You'd know how it works with IP. That was what they were looking at, not necessarily UV. I think you might be correct on the UV that we probably. I mean, if we did find a way, it's not going to be easy. But like in the infrared, where we get a lot of that absorption by the atmosphere, where they can background even the
that would be really useful.
Absorption lines, just get rid of them, like essentially turn them invisible, where we can actually correct for them. It's not. I don't fully understand how it's working, and yet it's starting to become like I'm starting to work on one of the areas that might branch off that way later. It probably won't be quite my work. It'll, but it is an application of the technology that we're using. They're fiber Bragg gratings, but I can't really say how they'd be used for that. I don't think. Not without chatting. So but it's just, let's say it would work, but you could remove that problem with the atmosphere. I guess that would make things better. You could probably spot some of these, but do you know of many bands in kind of the infrared that we'd be looking for in other planets?
Yes, I know in general it's easier to spot planets or even directly image them in the infrared. Because the infrared output of a star and the infrared output of a planet are much closer to each other in magnitude than like the visible light. So it's easier to like spot planets, period, and again, like actually resolve them as a point source, as opposed to just finding, detecting them spectroscopically. Blah. So, I don't know like the specific wavelengths off the top of my head. I'm pretty sure oxygen has some absorption bands in that frequency, although you'd have to worry about our atmosphere. There's a couple others too. I remember having a discussion about this and I can't remember them, but yeah, there are like gases of interest which do show up in the infrared.
Cool.
Yeah, it would be nice.
Eddie brought up something that I could be passionate about, but I won't get too passionate about Starlink. I would just like to say that Elon Musk can go suck a big one. I know what they're doing with other stuff is kind of cool and everything with SpaceX and that. But launching these satellites that are actually going to cause more sky pollution, fuck off. Please fuck off.
Oh, yeah. No, they are a nuisance.
I listened to a very good lecture where someone compared space, particularly like our kind of orbital area around the Earth space, to Antarctica, where Antarctica, because it's so fragile and you don't want to pollute it, is kind of more or less being given over to scientists, and they kind of control roughly who goes there and what can be placed there, and that has a really good effect of kind of preserving it, and you use it for research and finding out more rather than just any commercial thing like this. And I heard that they made a good argument on a similar grounds that perhaps we should look at doing that with space, where it becomes controlled more by like the scientific community, not like some dictatorship of scientists, but like for science it becomes, so it's not. Oh, sorry, you.
Yeah, as you say, there's already legal precedent for that, and I think the current like UN Outer Space Treaty, like you can't own space technically.
No.
Enforcement is another matter, but like you literally, it's considered to be held in common for the benefit of humanity. So yeah, that's probably the better way to approach it than just throwing up all these satellites and just kind of ruining astronomy.
Yeah, and I think it's like that's why sometimes, and it might just be a personal thing, I find it hard to get excited about a lot of these projects that the rich billionaires are doing, particularly when Richard Branson had his recent flight. It was just like, if the rocket is new technology that's going to help us in science, I would, but part of me was not probably as excited as a scientist as I think maybe other people found it.
Yeah.
Was particularly underwhelmed. No, I was particularly underwhelmed by Branson's flight because A, it's not really a new technology. B, they're not even going up into orbit. It's a it's a suborbital space shot. You're barely making it into space, period. And you're only up there for
the Germans in World War II had rockets that got to about the same height.
If you need to do science with that, you can do sounding rockets, which are a lot cheaper and have been used for 60 years now.
To be honest, Branson's all about rich person wank. This is about, I'm rich, I could afford to fly up and say I've been to space, because technically you've been to space.
I saw a poll someone made online. Should he be considered an astronaut? And the overwhelming response was no. The overwhelming majority of people responding were saying no. But again, maybe that comes back to it that astronomer is another area of science, and so comes with it a certain title that you have to earn. That a lot of the early astronomers were doing good work. They were going out into new fields, often at huge risks to themselves, whereas now I think, as you're saying, it's become more of like a tourist thing for rich people. Yeah. Very rich people. But then part of me is like, but if they bring more attention to the field and they get more funding to do that science... But I'm not sure that that's the best way to go about it.
I don't, at this point, I think Branson's probably doing more harm than good, because, he's not really doing any productive science. It's not even the first flight, because, Virgin Galactic has been doing test flights since 2004.
And not all of them successful.
Yeah, not all of them successful.
And they just bought out what was it, Space One or whatever it was called.
Yeah,
Bert Rotan's thing for the Project X.
Yeah,
or
Scale
whatever
Composites or whatever it is.
Yeah, Scale Composites. Yeah, you're right. Which won the whatever the competition was. An X program, a private X program competition to be the first commercial thing to get into space. And it's the Virgin Galactic ship is just a scaled up version of exactly what they.
Oh yeah,
they flew. Nearly 20 years ago, now.
Yeah,
it's not new.
So
There's absolutely
like
zero new about it.
Yeah, it's not really a huge breakthrough. So yeah, at first, again, I was very underwhelmed by Branson's flight. You know, Jeff Bezos is doing something that's a bit more technologically complex, but like only marginally. And also his company is running into trouble with their actual space stuff because they were supposed to supply engines for a new rocket that some of the other space companies are designing, the Vulcan, and they have not. And it's like becoming a seriously delayed program. So yeah.
I'm just going to answer Ox's thing where he's been going on about we shouldn't be spending money on space because we should be spending money on children and other welfare needs and things like that. We can have both. We should be spending money on science for developing technologies. The monies we spend on space have turn-on benefits to us as a society in the long term. Plus, the technologies we learn from that we apply to other things in our everyday lives. You wouldn't have Velcro if it hadn't been for NASA, or
a lot of other things. And so I think, it was as both of you were saying quite rightly. That's the problem we've had with some of these billionaires is they're not really advancing the technology side. But when it was done for technology, the technology we've got out of this has been incredibly helpful. And I would agree that, yes, if we have the energy to move humans to another planet for a colony, we have the energy to fix whatever problem we need to run away from. But if you look at NASA, like the list of inventions that NASA has had a hand in is so I keep forgetting very quickly, but everything from fire extinguishers to the mobile phone in your hand, the camera in the phone, most modern miniaturized electronics, came out of
shielded
the need
electronics.
To do it
only happened because
shielded electronics. The jaws of life, which you use to break people out of bad car crashes and other accidents where you can't otherwise get to them and you need to rip. That was a NASA thing. Space blankets, because that's where they get the name from. They're emergency blankets that you can use to keep people warm when they've suffered exposure to the elements. I start forgetting off there, but a lot of prosthetics as well, I think, came out of NASA.
Yes.
So science for the sake of science is, I think, a good thing. The more we know about the world around us, the further we can get.
The other thing that's worth noting is that, my master's is technically in environmental science. And, if you want to talk about sustainability, there is a lot space exploration can learn from sustainability and vice versa. Because, if we ever set up a colony on another planet, it's going to lead to like the most environmentally aware and sensitive generation our species has ever produced, because in that sort of environment, on Earth, if you spew out too much CO2, eventually, you ruin your climate. On a colony, if you spew out too much CO2, you die of asphyxiation pretty quickly. So, you have to be extremely aware and mindful of the waste systems your technology, your industry, your whatever is producing if you're in that sort of environment. And so, I think it would be, even from just like a point of how would this change human mindsets if, you have people who were raised in that sort of environment, and, are conscious of the impact environmentally of their actions in a way that I don't think any human ever has been before. So, I think that's something also to be said for the benefits of space exploration in terms of, actually helping fix problems on Earth. And the other thing is that if we ever want to do long duration space flights, especially if we want to do interstellar flights, we are going to have to get really, really good at sustainability. All the technologies we need are technologies that would be really beneficial on Earth and that we'd have to develop first on Earth here. So, again, there's a lot of opportunities for synergy in terms of like actually fixing real problems here on Earth, like water reclamation or waste, ultra efficient waste recycling and stuff like that. So it doesn't even necessarily have to be for space, but the technologies that we need here on Earth would also enable spaceflight anyways.
Yeah, there is one thing that Elon Musk has said, and it follows on from what you said. I know he wasn't original, but he originally the person who said it. Lots of people have said it, but he sort of popularized it amongst the things, and that is we need to become a multi-planet species to survive. Staying just on Earth, we will die out. We need to make the effort to get out there, to learn how to get into space, and to learn how to live in other environments, because not just because we're screwing up our planet. We can be smart enough to overcome that problem, but because the universe itself is not is not going to allow us to be here forever. One way or the other, we're going to get hit by a big asteroid, or eventually the sun will expand, or something else is going to happen. We might have another star come really close to our own solar system, and of course, if we are not a species that's got out there and got to other worlds and learned how to live there and become the aliens ourselves for those worlds, then we will not survive as a species.
Yep.
However, the timeline for that is quite extensive, which is my only issue with that. Like, in terms of the sun taking us out, like, we can't physically live in this solar system because the sun gets just physically too big and too intense. It is an order of about 5 billion years.
Yes.
And as for asteroids, we already have ideas of how we might deflect them. But again, this is why we probably want to look at.
But we still need the space technology to deflate asteroids. We are going to, if we don't do the space exploration, if we don't spend the money and develop the technologies and get better at it, we will something is going to destroy us one way or the other. Being multi-planet, having the technology to get out there and do these things is what will let us survive longer.
There was also, I heard an interesting fact, and I'm not 100% sure of it, but apparently there is it's quite rough in terms of, but there is still a cycle that the Earth goes through where you tend to get more mass extinction events every so ever many years, because apparently our wobble through the galaxy means we pass through a more dense band of roughly dark matter, so that you're more likely to get like asteroids coming in there or something like that.
There's been some debate about that, because like you're looking at fossil records, and is this actually a mass extinction, or are we just observer bias because we happen to discover more fossils from that era or what have you? But I think it's like every 100 million years or so. But regardless, the fact of the matter is that mass extinctions do happen on this planet. Not impossibly infrequently. They do happen from time to time.
Yeah, mass extinctions are just the biggest ones. There's so many. Like, if you think about, there's so many others that occur in the middle, and there's a good chance we're doing the worst one at the moment. The rate we're going.
Yeah, well, we caused this one. We didn't even need the help of an asteroid.
I think, is it humans in modern human history? So, not history, but like modern species. So talking biology here, that humans' existence. We've wiped out more than half of all the large mammals we've ever come across.
Yep. So, well, at least we probably. There's some debate about also the ice age was ending, so there was climatic shifts, but it's almost certain we did not help.
Yes.
Yes.
We are meant to be in a period of of cooling in the
We're not.
in the planetary cycle, but we have actually turned that around, that we're warming at a time when our orbital cycle should be causing a cooling effect. So what's it going to be like when we get the other side of that and we get the full effect?
Yeah, no kidding.
We have to solve these problems now, and part of that we can learn through space sciences as well, because we need the space sciences to observe what's happening with the sun. We could actually, one of the solutions that I'm actually really big in favor of building a partial Dyson swarm and sticking it at the Lagrange point between the planet and the sun and block off some of the heat that gets to us.
Yep. That, in terms of long-term climate
I
engineering.
think it's getting to it probably won't be as long as we would like before it does get to the point where we have to take some action like that, because we'll have done enough damage to our own atmosphere that it's not going to be sustainable unless we remove some of that incoming energy.
And we could remove some of the incoming energy by making other energy for us to use, which is ideal.
But one of the stat, I first heard this stat when because Dr. Carl got me to help him with some calculations. He's like our Bill Nye here, Tessa. He's one of he's probably the biggest science communicator in this country. I was helping him with some calculations. He wanted me to just double check some of the numbers with it, but apparently the Earth. This was back in 2012. These numbers, they're probably a bit more now. We're absorbing 400,000 Hiroshima bombs worth of energy each day, extra energy due to
Sounds
climate
about right.
change. So it works out was about 5 a second.
Jeez.
So
yeah, it's pretty terrifying. But it's not something that we as a species couldn't solve. With the political will and the funding, we could do this. The science is there. We can solve the problem. There just has to be
a matter of the political will.
Yeah, and of course the problem with the political will is, and I think it was said on Yes Minister a donkey years ago, it's more a case of a political won't than a political will.
Very true.
And that's brought about by part of the problem of how our democracies work. We elect politicians to serve a term, and at best most of them serve a couple of terms and then they're gone, so they only care about what's going to happen for the next 4, 5, 6 years, and after that it doesn't matter to them because they're not going to be there anymore. And that's in the nutshell is part of the problem, is that government is purely short term. It is not, it never considers the long term, and yet any of us who are in science, everything we do is long term. We're thinking about the things. It has to be long term because some experiments take a lifetime, and that's just the way it is.
Yeah.
So
Tess is further through her PhD than I am, but yeah, you don't do a PhD because you're a short-term thinker. You can't.
No kidding.
no.
Because it'll be about 10 years for you by the time you finish that you've been at uni or been studying, or
in one form or another. Yeah.
Yeah,
Proud of you, Tess.
but one of the things I guess one of the hopes is that the younger generations, like our generation, and the people younger than us, are much more on the ball with those problems. So it looks like maybe as time goes on, the will start to appear, because just in terms of the way they think, how they're educated, it is better. But then there's the other hand, is that it might be too late. That a lot of the people who are currently in power, it's not going to affect them to the extent that it's going to affect those who have very little power, because just that's how generations work. And that's a system. Like as you get older, you can work through your careers, and so the younger generations just by nature do that. But that's the only hope I've got, is that it does look like the younger generations are much more in tune with it. And that's globally. Yes, there are some places in the world where that's not the case, but overall, I think there's some hope. But I think it's going to be a matter of time. I think it's going to be a big race against time as to whether we start getting on that before it's too late. I mean, it already is too late in some senses to stop damage, but it's about...
Yeah, I think we're at the point now where we're going to have to be... It's not just a case of we have to reduce emissions anymore. We have to come up with solutions that are going to help us, and they're going to have to be technological. We can't just. We're not going to solve this because it's going to take too long for the planet to recover unless we help it. And that's going to either be some way of blocking out some of the sunlight that gets to us. Perhaps we have to come out with our own. We need to come up with better power sources. So perhaps we can industrially remove CO2 from the atmosphere. The plans things like that.
Or other ideas are to literally start making the Earth shiny, like you coat parts of the Earth and certain things, so you make cities colors. So I mean, this is why science for the science's sake is so useful, because you don't know where it's going to lead, but where it leads when you average the system out is always beneficial. It never
and if I'm going to be honest, science is completely underfunded. I would like to see every nation in the world cut its military budgets in half and give that to science, because that would be awesome. You imagine what we could do with that. It's not going to happen, but I would like to see it.
Now, just the dream of everyone holding hands and dancing around a sunny hilltop.
Yeah. World peace and all that. Yeah.
It's probably not going to happen.
It's not in our lifetimes anyway. But I'd like to see a move in that direction where we're going, let's take money away from these things that really aren't going to help us survive longer as a species. Think about us as a whole, as a species. Even if you want to be arrogant enough to say, don't give a shit about the other species on the planet. Us as a species, you've got to. If you start with us, we have to have the other species to survive, because they are part of our ecosystem and they're important to our ecosystem. And if they die, we lose that ability. If the plants start dying, we don't breathe. If the oceans start dying, we also don't breathe, because the oceans are a big thing that recycles CO2 for us. Yeah. If the Amazon it dies out, that's it. We're dead. So it's one of these things that if we don't work on these things, if we don't support the planet, we're the ones who will eventually die. We might be the last ones in the chain, but we will die. And that's it. And you can go, it's all right, it's going to happen to my grandkids. Yeah, if you say that for a second, that it's going to happen to my grandkids, it's fine. You're an asshole. Yeah, I get vocal sometimes. I'm ranty. Sorry, Tessa.
Hey, if you're going to be passionate about something, this is a good thing to be passionate about.
Yeah. But hopefully we can fix the problems that we're facing. I mean, humanity is good at solving problems, and we have a problem in front of us. We can solve it. Using problem every second word here. The issue is that we don't solve things until they are a massive problem.
Right.
Yes.
I think one of my favorite quotes from Winston Churchill, and it is, we can always rely on America to do the right thing once it's exhausted every other option. And I would like to change that to just humanity.
Yes,
humanity. Nope. I've had that thought as well in reference to that quote, because it's very descriptive.
I mean, at the time he was correct about that phrase.
Yes, but it does stand for humanity as a whole. It tends to be our attitude. And why put off till tomorrow what you can possibly put off to the next generation? Seems to be the motto of us as a species. We're quite fine with things being somewhat in the future, and we can't always do that.
There's probably a good genetic wiring for it. It's probably not necessarily our fault.
Oh no! There's probably some evolutionary thing, but we have to rise above our evolutionary programming and be better than that. We have to see that the things we do now matter, and we have to work towards solving the problems that we helped create. And I don't care that if it was our parents that created it, or our grandparents or great grandparents back in the start of the Industrial Revolution. It doesn't matter. We as a species created this problem. We are destroying the planet that we live on. We need to do something about it.
Yes. If we want to keep looking for life elsewhere,
we have to save the life
down here.
Yep. Very, very true. Very true.
Or else we will be the life. We will end up being the life that is found by some alien species in the future, and they'll go, "I wonder what they did." And that's assuming there's any trace of us left, because they'd have to find us in the next 20,000 years, or else we're pretty much wiped off the planet. That's how fast it happens. Things just, the planet eats it all back up again. Ultimately, you end up with virtually no sign of us. I mean, the only thing that they'd know for sure is, hey, they obviously had nuclear weapons at some time, because that's going to stay around for a really long time.
Actually, that brings up a good point. I kind of want to ask Tessa your thoughts on this. Is what if that happened? The actual evidence for us might not be on Earth. It might be what we leave behind on the Moon and on Mars with all the probes, because those will last a lot longer.
Oh yeah.
Here.
I mean, there's a reason like they have, a lot of the things we send out have plaques on them, because like they're basically time capsules. And some of them, like, even have, like, the shape of the Earth, of its continents, at the time the mission was sent. So, like, if anyone else finds them after, 5 million years, they can, approximate when it was sent based off of, working plate tectonics backwards.
The interesting thing about that, especially if you're talking about Voyager, the two Voyagers which have both left the solar system, and I think the Pioneers are out that way, out that far as well now, even though we don't get signals back from them anymore, is that if they are found in the next about 36,000 years, it's going to be us that finds them.
Probably.
Because that's how long it's going to be before they get to the nearest possible stars, and we're more likely to be the ones who go out and find them, just to see how they fared being in space that long. So
could you potentially, if let's say it goes the other way around and a probe comes here, could we could probably track roughly where it came from, couldn't we?
Yeah.
We'd have,
based off its velocity and trajectory, we could at least have a rough idea of like where in the galaxy it came from.
Life was here, but they did a human.
Yeah.
And took themselves out. Oh, I think communication would also be a problem, even if they were still around by the time a physical probe like that arrived. Unless they were much closer than we thought.
Yeah. This has been absolutely wonderful, Tessa. We're going to have you back on, but Matt and I have been going for 2.5 hours now. So we might actually start winding up now.
Yes,
it is very late.
2:20 in the morning.
Yeah, it's 2:20 in the morning for Matt. So I think we might wind up. But this has been brilliant. Okay. I'd love to have you back on again sometime, Tessa.
Oh, absolutely. Yeah.
And we can discuss this stuff a little bit more, because it's been absolutely fascinating. And I'm sure Matt's still got plenty of questions for you outside of the stream as well. Yeah, I know he wants to pick your brains to help with his thing.
I could ask questions on science to anyone all day. Trust me, I can talk for hours and hours on this stuff.
That's why Matt and I wanted to do this, because we like getting our geek on and talking to other people who into science and any form of science, especially if it's something that neither of us are experts in, because that educates us and it educates our audience. And
right.
I always say that I love being wrong about something and being corrected, because then I know I've learned something. And I think that's true for all of us. That the more we can be corrected by people, the more we can hear new things and get the bigger picture on something we might think we know a little bit about, but we haven't quite got there. The better it is for any of us. And that's really my aim. And I know it's Matt's too, is just to educate and to lift up. And I know that's yours too, and that's why you have a podcast. And
I do, yes.
You do. So tell our audience a bit more about your podcast.
Yes. I am the co-host of Assigned Scientist at Bachelor's, which you can find on all of your podcast platforms, as well as at
the links below in the description.
asapodcast.com. And it is a podcast that is dedicated to interviewing and highlighting the research of trans and non-binary scientists. And, we have people in all sorts of different fields, from physical anthropology veterinary medicine, physics. Haven't had any geologists on yet. We're working on that. A lot of biology people and astronomy people as well. And we also talk about Star Trek from time to time too. Just seems to come up.
Of course, you got to talk about sci-fi.
So yeah. Oh yeah. So anyways, yes. If that would be something any of your listeners would be interested in, I definitely recommend that they check it out.
Please do. As I said before, the link's down in the description. Please follow Tess on Twitter and go and check out the podcast because it is really, really good, really, really interesting. And as you've seen from this, Tess is quite amazing. Her knowledge is brilliant. And the more voices we can get out there and people can hear, and the more you can learn about science all the time, all the better. And a lot of the people Tess interviews are really, really interesting people. So, yeah. So, when's your next podcast actually, Tess?
I am not in charge of posting them, although we just had one posted yesterday.
Oh, okay. Who are you interviewing?
We try to do every other Thursday or Friday. Is usually when my co-host gets around to posting them.
I'm behind on them, so who
some
did
weeks
you
are
last
better than
interview?
Others. The last person we interviewed was Dr. Theo Tiffany, who was talking about sort of drug development, specifically for like hepatitis C, both in terms of like the medicine of it, but also in terms of like from a public policy point of view. How do you develop a treatment that most people can afford? How do you get it to the people who need it, etc.?
Oh, because hepatitis has become a major problem in some areas of the US, hasn't it?
Yeah.
A resurgent, and part of that is healthcare in the US not providing that. So if you can get it out there cheaper and quicker to people, you're going to bring that down. That's brilliant. So go watch it, people. Go watch it. So Matt, you're still working on your new doco, which will be covering.
That one's going to probably take a while. This one's going to be quite a full-on one.
Which will be covering more of the stuff that we were talking about here, and I'm pretty sure there'll be a little thing at the end of it with the special thanks to Tessa for helping, because I now know you're going to pick her brains. Have you got anything else coming up, Matt?
Keep going.
Matt, have you got anything else coming up?
That's the main one I'm looking at.
That's the main one you're looking at. Okay, so next week, I'm hoping, she hasn't confirmed yet, but I'm hoping we're having Maddie from Science Side Up on. And we'll be, if it is Maddie, we'll be talking more about climate change probably, and nuclear physics, because they're kind of her field. Yeah, you are so excited, aren't you, Matt?
You said nuclear.
Oh yeah,
No. In terms of like, you get excited by any
science.
But it's easy to get excited. It's science.
It's science. Yeah, everyone should be excited by science. That should be our tagline. Everyone should be excited by science. But yeah, so expect that there will definitely be another Schrodinger's Bathtub next week. There is not a What the Fuck show this week. In fact, there may not be another What the Fuck show. We're looking at shelving it to do other projects. And I will talk about more of that later. I will probably do a roundtable discussion during the week to discuss other things that are happening on the channel. But yes, please, everyone, go and sub to Matt. Go follow Tessa. Go check out the podcast because it's amazing. And again, thank you so much, Tessa, for being our guest. Thank
you for having me.
Oh, it's been
a joy.
And it's been an education as well. And thank you, Matt, my wonderful co-host. And thank you to everybody out there who's been watching. It's been an amazing audience, despite the fact that we had Darth Dawkins come and troll us earlier. This has been a brilliant stream. We look forward to sharing science with you more. And have a brilliant evening or morning or wherever you are in the world. All right. Bye, everyone.